Welcome back. In last part, I discussed two important problems. In this part, I will discuss one important concept, which is our intensity of radiation. Let me change the color actually. Yes, intensity of the electromagnetic radiation. Okay, we are very familiar with this term, right? Intensity. Let's say if we consider a classical mechanical wave or sound wave, if it is a transverse wave, then the wave is like this, right? So here this is the amplitude, this is the amplitude, it's y, it's x, then y should be some sign, should be some amplitude x naught sine omega t minus kx plus phi in general form is this like this. So this is the amplitude x naught, right? So we know in case of this mechanical wave, we can write down the intensity is actually proportional to the amplitude square, that means proportional to x naught square. Okay, so it is the intensity. But here for electromagnetic radiation, we have to find out the intensity. What is the definition of intensity, and we have to evaluate the form of the expression, mathematical expression for the intensity. Okay, so we know that, let me go to the next page. Okay, we know that the electromagnetic wave is also a propagating wave. So let's say this is a electromagnetic wave. Okay, first I made this. Okay, we are considering a cylinder. Okay, write this is a cylinder. In the electromagnetic waves is propagating in this direction. This is the electromagnetic wave. Let me draw it. Okay, so we are considering a plane. We are considering a plane perpendicular to the direction of propagation. Okay, in this direction the electromagnetic wave is propagating. This is a plane, and let me consider a point P here, any point P. Okay, so what will be the intensity of that radiation? This is our electromagnetic wave. Okay, so the definition of intensity, let me first write it. The definition of intensity, the general definition of intensity is, okay, amount of energy per unit area per unit time. Okay, so let's say this area is the unit area, this area, surface area is unit surface area. If we consider, then the area is 1 unit area. It may be in CGS or SI, but it is 1 unit area. So that means the electromagnetic wave is propagating, right? So if we consider a plane, let's say there is a plane, in this way electromagnetic wave is propagating, and here is a plane. So how many total amount of energy is per unit time, per unit area is the electromagnetic waves imposed in that plane, that is called the intensity of that electromagnetic waves. Okay, let's say here there is a P point here, as it mentioned here, we are considering this is a P point. Okay, so at unit time we know that the velocity of the electromagnetic wave is equal to the speed of light, which is c. So at unit time we can consider that the this length should be C, the length of C, the cylinder of length of C will impose its energy to that point, okay, the point P, that should be the equals to the intensity. Okay, let me clear again. So intensity I should be total energy divided by area into time. So we can write it total energy per time divided by area. So we can write it total energy in the cylinder of unit surface area having cylinder having unit surface area and length of C. Okay, we can write it. So here let me state it. The intensity of radiation of that imaginary cylinder at point P is equal to the energy incident per second, that is the energy stored in the volume. Okay, so we can write it here. What will be the total energy? This is the cylinder, right? This is the cylinder of the length C and the cross section area, this area is unit area. So the definition is consistent. So the total energy stored in this volume should be the intensity of that radiation. Okay, because as I mentioned before, the intensity should be the total amount of energy imposed at a point P perpendicular to the plane of that propagating electromagnetic wave per unit area per unit time. So we have considered cylinder from that electromagnetic wave which has the unit surface area. Then the cylinder of length C obviously will having the length of C and having the length unit surface area 1. Then we can say that the total energy stored in that cylinder should be the intensity of that electromagnetic radiation, right? So we can write it here. I should be total energy stored in the cylinder. What should be? That should be energy density into volume of cylinder. This is the energy density, correct? So it should be like this, because we know that if we multiplied total volume of the cylinder with the energy density, then essentially we will obtain the total energy. That is the definition of the energy density, right? So it will be U, and what is the volume of the cylinder? That is C into area, which is 1. So it is U into C. So intensity should be U into C, and we know that we know the form of U, right? Here, this is the form of U. This is the U. This form we can take. So from here we can write that I should be 1 by 2 epsilon naught C E naught square equals to, we can write 1 by 2 mu naught, again C will be multiplied B naught square. Okay, yes, or we can write it 1 by 2 mu naught C H naught square. So this is the intensity of the radiation, electromagnetic radiation, right? Okay, so actually the definition of intensity is actually what, again let me write, that is the amount of energy per unit area per unit time, right? So this is actually the definition of flux. Okay, this is actually the definition of flux. So here also we can write it in terms of flux, which is denoted by S. This is the flux. So flux is S is du a dt, as I write it now. This is the intensity, like total energy divided by area into time, the same thing, total energy du area time. Okay, so here u is the total energy. So this is the definition of the flux. So this should be equals to cu, as I derived here, u times c, that should be equals to u times c. This is the definition of the flux. Okay, so what will be the average? If we consider the average flux, then it will be like this. Okay, and we know that, as I state here now, for a complete cycle we can impose this condition. So under that condition it is consistent. Okay, so it is the average value. Now let me discuss the Poynting vector, right? I discussed last class little bit Poynting vector. Here let me discuss in detail. Poynting vector is also denoted by S. It is defined as 1 by mu naught, or we can write it just by this. This is the Poynting vector. Okay, we all know that in electromagnetic waves, the direction of the propagation of the electromagnetic waves is perpendicular to both of the electric field and the magnetic field. Okay, if we draw it again, this is the direction of propagation, which is denoted by the S vector. We will see it why. Let me first write it, direction of propagation. Okay, and this is our electric field, let's say, and in this direction the magnetic field. So we have drawn this figure several times, right? Okay, so this is our electronic radiation. Now here the Poynting vector is defined like this. So E is in this direction, z axis, through the z axis, B is in this direction. Then what will be the direction of E cross B? E cross B should be in this direction, right? Okay, z axis, if we apply the Fleming right hand rule, then E cross B, it will be in this direction. Also we can this is along z direction, this is along y direction, so it should be along x direction, right? Which is essentially the direction of propagation. So the Poynting vector actually denote the direction of propagation of the electromagnetic wave, which is defined by this. So this is actually the direction of propagation, it suggests. So this is the definition of Poynting vector. Okay, so let me write what was the formula of intensity. If we summarize it, it will be u times c. But we should keep in mind that this definition is valid for only free space, vacuum. In free space only the speed of the light is c, but in general the general form will be I is equal to u times v, which is v is the velocity of the electromagnetic waves. As we discussed in the last class that if we change the medium, then frequency of the wave, electromagnetic wave, nu will be fixed. It will not change. It is fixed. But lambda and v changed. Okay, so lambda and v will be changed. So that's why I written here V. So this is the general definition of the intensity. So we know the U. So in general form of the I will be I is equal to 1 by 2 epsilon naught V E naught square divided by half into mu naught V B naught square. Okay. So and the form of the V is 1 by root over epsilon nu. We know that the form of C is 1 by root over epsilon naught mu naught. This is for free space, vacuum. If it is not free space, that is a medium, then it will be reduced to like this. So this is the form of the velocity. So also here we can replace the value, but this is a general expression of the intensity here. Okay. Now the unit, what will be the unit of the intensity? That is also important question here. So unit, what will be the unit? Okay, intensity of the electromagnetic radiation, I, what energy divided by, if we pose energy, unit of energy divided by unit of area divided by unit of time, it should be like this. So what is energy? Joule, area is meter square, and time is second in obviously SI unit. So it is this. This should be the energy of the intensity, or we can write it Weber per meter square, where Weber is joule second inverse. Okay. So the dimension should be what is the dimension of energy? It is m L square T to the power minus 2, and area is L square and time is T, so it will be m T to the power minus 3. This is the dimension. Okay. So it's all clear. Now we'll just briefly introduce the radiation pressure. What the radiation pressure is signifies. Okay, in this part let me stop here in an intensity part. This is the general form of the intensity valid for all medium. If it is free space, then it will be V will be replaced by C. Otherwise, this is the general form. So in next part, I will discuss the radiation pressure, and I will do some numerical problem as well. Okay, thank you.